Good morning. We're going to go over 94 and 95, so let's do it. In question 94, I'm loving it. I finally have my chi-squared test again. And this time, you can see here, I swapped out the word M&M because it absolutely looks just like an M&M problem, which we know is a chi-squared goodness of fit. So it says here, a geneticist hypothesized that half of a population will have brown, and the remaining half will be even split between blue and green. So that's kind of like calling M&M and saying, okay, what should I be getting? The geneticist says half. And so they say what that means is if I talk to 60 people, I would assume half or 30 would have brown, and then the remaining 30 would be split. So these are my expected values, and this is really similar to my M&M question. So I always tell students, of means multiply. So 50% of 60, and then half of a half, so that's 25% of 60, and 25% of 60. So to calculate the expected values of each of these, brown eyes would be 50% of 60, or 30. Blue eyes would be quarter of that. Half of a half is a quarter. A quarter of 60 is 15. I think you get the point. Now we can compare these amounts, and I actually did this by hand using the formula right off of the formula sheet. You totally don't have to do this. You can completely, here it is, there's the chi-squared calculation. You can type this into a two-way table, so I can show you how to do that as well. You turn it on, you hit the home button, you go to the make a table screen, and you put your observations, eyes, I'm going to call it O-B, eyes, E-Y-E, and type in those numbers, 34, 15, 11, and then you can go right next door. Goodness of fit, you have to calculate the expected. So I'm going to call that EX, eyes, E-Y-E. So I expected to get 30. I got 34. I expect to get 15 green. I got green. I expected to get 15 blue. I got 11. So looking now at my table, I have my observations and my expectations. Now I can do a chi-squared test goodness of fit. So I go to a stat test, and I find my selection chi-squared GOF. It asks for an observed list, so that I called OB-eyes, O-B-eyes. It asks for an expected list, right? And I called that EX eyes. My degrees of freedom. So my degrees of freedom would be number minus 1. So that would be 3 minus 1 would be 2. So I have 2 degrees of freedom. And I'm going to hit OK. So my chi-squared value I get in my calculator is 1.6. Now, I also get a p-value that way, so I can decide what door to walk through, but that's not what they're asking in the question. Now also, this is very straightforward to do by hand. Observe minus expected, squared over expected, and then there's our summation, sum it all up. So I observed 34, I expected 30 brown. Squared over 30. I observed 15, I expected 15 green. Squared over 15. I observed 11 blue. I expected 15. Squared over 15. Remember that the denominator holds all of my expected values. And then when I add up these fractions, I end up getting 1.06 repeating. Remember, that's what we got on the calculator to begin with. Next question. A small town employs 34 salaried non-union employees. For each employee receives an annual increase between $500 and $2,000 based on the mayor's staff performance review. Some employees are members of the party and some aren't. So they're trying to determine if groups that got a raise A or a raise B were in the party. Were they in the mayor's party or not in the mayor's party? Interesting study. So the students from the high school formed the list, one for the raises granted to employees who are in the party and the other list for those who got raises who were not. They want to display the graphs showing the salary increases. So I kind of made this table to just kind of sort out how maybe they'd collect the information. And then I wrote down here salary increases. So I could show this in a table or a double bar chart. I'm sitting here, you could see I'm kind of scribbling around saying to myself, how else could I display this data? Maybe in group A, group B, and I can show salary increases as a back-to-back stem plot, A and B, right? So A is possible. A scatter plot sounds terrible. We wouldn't take this data. Well, think back, like when we were comparing machine A and machine B, we don't do that on a scatter plot. Could I do it in parallel box plots? I think I could do that. This would be the raises of A, the raises of B. A histogram, I think I could do a histogram as well. This is just kind of a histogram sideways. A back-to-back stem is could turn into a histogram, and I can see the distribution of A and see the distribution of B. A dot plot, well, a stem and leaf plot kind of looks like dots. You can think of each stem as a dot. So all these are good. The one that doesn't make sense at all is this scatter plot. That's my answer. Thanks for joining us.